Welcome to today's webinar. The topic today is seismic displacement limits and seismic design of buildings in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the webinars, the technical content of the website, customer projects, and so on. I will be the moderator today, and I will answer your questions together with Thomas Eichner. The presentation will be done by Victor Hidalgo. My two colleagues are the main responsible persons for the development of the dynamic add-ons. And I wish you a nice webinar from Victor. Then I say something how you can ask questions, at least for the attendees who participate the first time. I switch off my webcam that you can see the full screen. You can press the button with the question mark, then enter your question in that field, press send, and we will receive your question and we will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Victor. Victor, you can start.
So thank you, Andreas, for the introduction. And from my side, also welcome to today's webinar. The content for today is divided in 4 main topics. So the first one is a small introduction to the topic seismic displacement limits for buildings. Second place, we will see how the procedure with building model in our program is, and we will use this building model add-on for the automatic definition of modeling assumptions and results. In third place, we will see what we can get in the program without the add-on building model. And in the last place, a small conclusion about iteration process in RFEM and information on optimization in RFEM, so related to seismic displacement and seismic design for buildings. Okay, so let's get started with the first topic, the introduction to the topic seismic displacement limits for buildings. So the reference for today will be the Eurocode 8, design of structures for earthquake resistance. So this reference applies for the whole Europe, particularly maybe in countries like Germany or small seismicity countries is not that relevant, but we will make here an exercise or an example in which the seismic displacement is the controlling action or the seismic action. Okay, so I just want to remark that I'm gonna present here several sections from the Eurocode 8, but all the requirements are not exactly what I show here. So what I want to say is that this summary can be understood as a good pre-dimensioning tool, or a first iteration procedure, but further requirements and sections have to be complied according to Eurocode 8. So it is recommended that a full review of the norm should be taken into account. As I say, this is maybe the first steps for these checks. Okay. I'm going to start with 2 sections so that maybe we'll know, but if not, I'm going to explain very quickly. So these are the horizontal elastic response spectrum and the design spectrum. So I made here a quick summary with the equations, and for the elastic we have the base values or the base equations. For the design spectrum we divide by this factor Q. Q is the behavior factor. It's a description of the structure and it depends on material. ductility class and irregularities in general. So it's a good summary of our structure. Exactly. And so the second section, or better, the third section here for the introduction, it's gonna be the displacement calculation according section 4.3.4. So I will start with the part or with the value d sub e, and this is the displacement determined by a linear analysis based on the design response spectrum in accordance with 3225. So this is exactly what we just mentioned here. So this is the displacement using the design spectrum, and what this section tells us is that we have to multiply by q sub d, and this value is normally assumed equal to q. So what we make here, so it's a multiplication of the displacement calculated based on the design spectrum. Yeah. So I prepare here a figure to try to explain why this multiplication has to be carried out. Yeah. And let's assume that the black line is the elastic response of our building or our structure. And of course, we know that at certain point we will have inelastic response in our building. Yeah. So this inelastic response can be described by a model, in this case a bilinear plastic model, or whatever we have here as a model, but we have some inelastic action. Yeah. And the ratio between elastic and inelastic forces can be summarized as this behavior factor Q. Yeah, that's what Q tells us on the axis of force. And let's see now what happens on the axis of displacement. Yeah, so at certain point we have the elastic displacement, and if we say here, where is here our inelastic displacement? So this is gonna be approximately on the same magnitude or range of values. So one can say that the elastic and the inelastic displacement are gonna be around the same values, while the forces and internal forces will have the ratio of Q. Yeah, and this Q is the summary, as I said, from the structure, but also the summary of the inelastic response and energy dissipation and all these mechanisms that take place in the inelastic response of our building. So this is a topic of earthquake engineering, so quite advanced topic. Maybe we see here just the sections with a very straightforward procedure, but this is kind of the concept behind it. Yeah. Okay. So maybe if it's not totally clear after the presentation, you can read more about it and try to have this picture as a reference. Okay. Now I jump to the third section here. It's the limits of the so-called interstory drift. So in the first place, here a picture about what's the interstory drift. So it's the relative displacement between the top of the story and the bottom of the story. So we have to control this measure of displacement in each story, and not necessarily in overall of the structure. Okay, so we have three limits, and so the limits are for dimensioning and design of structural elements, but we see that the description or the classification, these three limits depends on the description of the non-structural elements. So it's very important to take into account that from the beginning, in the prefactibility, prefeasibility, or other or early stages of design, it's quite important to define what's the description of the non-structural elements. So if we have brittle materials, so we have certain limit, and just the description of ductile non-structural elements might be so really important for the construction site, and maybe the costs of these non-structural elements according B or C might be too high, and we have to switch to approach A. Okay, just quick summary here. This factor on the left side is 0.5 for importance classes 1 and 2. So we can rewrite these limits in this way. So that's on the limits. We have here a reference about this result in order to compare. And this is another important section, and it's the interstory drift sensitivity coefficient and P delta effects. So we will calculate this also in the program, and we check that either one of these three conditions should be taken into account or satisfied. Yeah? And once again, we see here another reference to our second section 4.3.4, which means the multiplication of the displacement based on the design spectrum. So, okay, let's start on the second chapter of today. So the procedure with building model. So I have 4 steps and then a couple sub steps. I'm gonna once again present here several sections from the norm, and after that I'm gonna jump in the model. Yeah. So let's check out here 2 sections, 2 important sections. The first one, okay, the first step, model analysis. So based on an available model, we will define a model analysis, and after that a response spectrum analysis. But for this, we want to take into account the stiffness according 4.3.1 and the subsection 7. Yeah? And that's why I started with this figure in the introduction. So this section recommends that the stiffness when the cracking takes place should be taken into account. So, and this cracking takes place in this inelastic response now. So if we say at the red line, it's gonna be the actual response of the building. So at this point we expect some reduction in stiffness, and the recommended value is to half of the corresponding stiffness of the uncracked element for shear and for flexural stiffness. Now for both of them we should consider the half. And another important paragraph or section is the primary and secondary seismic members definition. So secondary members are members not forming part of the seismic action resisting system of the building, but beyond this definition, it's important to say that such elements do not have to comply with sections 5 to 9, which can be very important for detailing in the case of reinforced concrete elements. So the detailing is way more, or in steel we have additional requirements for buckling or this. No, so this is also very abstract. I'm gonna show a very simple example in the program, and let's take a look for these 2 sections in the program. So I'm gonna start with a description of the building. So we have a very irregular building here. We have jumps in the geometry of the stories, and I did this in purpose to illustrate the concept of irregularities. Just as a quick description, we have here a reinforced concrete building with walls, and one can say very stiff walls. I'm gonna show them here with visibilities. In the navigator views, we have some predefined visibilities which help us with the inspection of the model or visualization. Yeah. So we can see here 6 walls which are conceived to limit the lateral displacement of the structure. So exactly this interstory drift. Okay, I'm gonna cancel the visibility. I come back to the original view, and I am gonna show the loads definition. So I have 2 load cases, self-weight and superimpose on live load. In this case, I have a very general definition, quite simple for today's exercise. Yeah, of course. So that's our base model. Also, just to say, the first 2 stories have a height of 4 meters, and after that we have 3.5. So this is gonna be important when activating the building model. Okay, so we have this general overview, and now we want to define our model analysis. For this, we will go to the button Edit Model Base Data, and here we can activate the desired type of analysis. In our case today, dynamic analysis. If I click on response spectrum analysis, model analysis will be automatically activated. And according to what I want to calculate, I can select others add-ons. In this case, it's just of interest, this dynamic analysis, and take into account that when we activate something here, we might need to provide a norm or a design standard for the corresponding new feature in program. So in this case, I'm gonna leave Eurocode. Okay. Now I can go to edit active load case. In this menu, I can create a new load case of type modal analysis. Yeah? So I'm gonna call it modal analysis 1, and this is gonna be basis 1. Okay. I'm gonna edit the settings. I erase the second, and I'm gonna make here a typical definition for modal analysis to reach effective modal mass factors, typical value of 90%. And then we are limited to this method for solving. Yeah. On the mass matrix settings, I'm gonna choose diagonal on a classical building analysis with the 2 horizontal components, and just the theta component, so the torsional component. Okay. Apply OK, and then we have to select a proper import masses only from load case load combination. So each code defines the kind of combination of vertical loads that has to be selected here. I'm gonna show how to do this from scratch. So this means here in base, in the tab base, we can activate our combination wizard and or assistant. And with this, we can automatically generate combinations according to the norm, the selected norm, in this case, Eurocode. Okay. In design situations is the basic definition, and we select here, for example, seismic mass combination. With this, we will get subsequently here in load combination the corresponding factors and multiplication according to the desired design situation. Yeah. Here in assignment, we see a factor of 1 for self-weight and superimpose, and live load with 0,3. So that's according the norm. So that's quite useful in our program. Here we can go back to the model analysis, be the first place, apply, and then we have available our combination. Okay, perfect. So after this, I can define a second model analysis, and we are gonna do the following thing. So this is gonna be the basis. In this case, we are not considering any of these two sections. Then we will make a second iteration with just the 4.3.1, and then a second iteration with these two sections. Yeah. Okay, let's do that. So I'm gonna copy this one. Okay, and after copying, I'm gonna change the name to 2. I erase this here, and I prepare in advance a structure modification. Yeah. This is quite a very useful tool in our program, and it's very useful in this case. So I have 2 definitions. I'm gonna show them. So here you can activate what you want to have, in this case members and surfaces. And for members, I made the following definition. So according the section in the norm, there is a reduction of 50% on the shear and bending stiffness. Okay, and I selected practically so all elements. Okay, I'm gonna copy the section just to have in mind the section or what we are doing. Exactly. So this is the second model analysis, and I'm gonna create a tier 1. And here I'm gonna select the second structure modification. I'm gonna show them. Sorry, in the first structure modification, I forgot to show the surfaces definition. In this case, also a 50% reduction. So this stays the same in the second structure modification. And in the case of members, I have this difference. Yeah, so I have a second definition in the structure modification number 1. I only have 1. I'm gonna show this. The first definition inside the structure modification remains the same. And in the second definition, I try to take into account this section. And what I did here is to make a strong axis definition of stiffness in the member. So this is the bending stiffness. I'm ignoring the bending stiffness around the strong axis for certain elements. And which elements? These are what we can call secondary beams, yeah, or just vertical beams. So I'm gonna show in program what's the effect of not considering these elements that do not belong to the main earthquake resisting system, yeah, or lateral force resisting system. Okay. And here I can write the second paragraph. Okay. So we accept this and we can run the model analysis. It takes around 30-40 seconds for each model analysis. So I already did it for today's presentation. I'm gonna show that the definition is exactly as we did before. Yeah. Okay. And we are gonna take a look on the model analysis results. Yeah? So here on the table, we can go to model analysis, natural frequencies, and we see for our iteration number 1, a natural period of 0.9 and 0.7 6. Okay. If I change to the second iteration, so the stiffness reduction, we will see a huge change in the structure, so from 0.92 to 1.24. It's a quite big difference, and it's very important to always keep in mind this requirement about stiffness. So it's a typical or classical assumption in earthquake analysis. And here we can see how different this is. No? And this is quite different approach in comparison to design just for vertical load. No, we don't do this normally in the vertical load. Okay. Model analysis. Number 3. Here we have the consideration of the second elements, or the not consideration of second elements. So in this case, we add that the secondary beams, yeah, I'm gonna show them here. Members, cross section. Okay, so I'm saying that all these secondary beams will not have a flexural stiffness around the strong axis. So in order to avoid their participation in the lateral stiffness, as we expect, these contributions shouldn't be that big. Yeah, they do not connect to any column. Yeah, we don't have any system. Yeah, there is no frame, and we can see that the result remains almost the same, just small change on decimal places. Yeah. Okay, so after this, I'm gonna work with the load case 5. Yeah, this is gonna be our reference, and just here, just to show you how you can inspect modal analysis results. So quite important table here, effective modal analysis masses. You can see here, for example, if you want to display the deformed shape of a particular mode, you can see here, maybe in this drop-down menu, you can select what you want to display. Okay. Also important, the factor for effective modal mass here. I selected this geometry to show a very particular effect when we have irregularities and when we also have a very stiff element such as walls, or the so-called shear walls with frames. Yeah, this interaction plus the irregularities create this particular condition where the fundamental mode has a participation of 50%. Around 50% is quite low, or relatively low. We are used to see here maybe 70 or 80%, and with particular conditions in geometry, we can see that the second order modes are quite important in the response of our building. Yeah? Okay, just wanted to show this. So now I want to define a response spectrum, yeah, according to the content in the presentation. Okay, here. After doing this modal analysis and this stiffness and primary and secondary definition, so we can make the definition of the horizontal elastic response spectrum and design spectrum. And here it's important to make a definition of the behavior factor. The behavior factor is defined or specified in section 5.2.2.2. So I recommend a review of this section, a full review. And in this case, for our concrete structure, I made a definition. Yeah. How this works is that according the location and according the norm in the for a particular country, it is defined which ductility class or which kind of requirements I do have to fulfill for this particular place. No, for example, in Italy, high seismicity, I have to select a structure that fulfills particular requirements. So this is provided by the norm. Yeah, because of time, I cannot make a full explanation on this. But let's assume that according to the location of this building, I have to use ductility of type middle class ductility. And based on the description of our system, we have a dual system, coupled wall system, and this is the base definition for our behavior factor. Yeah? And as we see here in the title, it's for systems that are regular in elevation. So I can calculate the first or the basic value of the behavior factor, and after that I have to check for irregularities. In this case, the building is irregular. As I say, I recommend that you check out after the presentation the section in detail, but here a definition. So Eurocode formulates a reduction of the 20% of the behavior factor if regularities take place in the building. So that's why I get this 2.88, okay? And I'm gonna make a definition based on this, on the program. Okay, so I jump in the model again, and I'm gonna make this definition. So I changed the analysis type. Oh, sorry, I copy. I'm gonna do this again. I'm gonna create a new load case, and I say, okay, response spectrum. And I'm gonna make this with a behavior factor of 2.88. Okay. On the definition or on the settings, it's important to select here the model combination method. I'm gonna leave it by default, and maybe here absolute sum. It's not that relevant for today, but just keep it in mind. Yeah. And the model analysis it requires. So we are gonna use our load case 5, our final iteration, let's say. We are gonna consider accidental torsion, and the program automatically defines or identifies which measures do we have over there. Yeah. We can adjust this by going here inside and maybe select 2 points. Okay. Here, oh, sorry for this window. Okay. I continue here. Okay. So we can adjust this, yeah, here on the program, but in this case, I'm gonna leave it by default. And now I can go to response spectrum. I'm gonna activate horizontal components, and I go for the definition here inside. Well, I had it previously, but it's our 2.88, and I select this reference peak ground acceleration in order to have certain values in the interstory drift, but according site, we can define the ground tip with geotechnical analysis, and the reference peak ground acceleration, it's gonna be read from acceleration map, yeah, provided by the norm. I just say okay, and okay, I'm done with this definition. Important here also is to create a second response spectrum, and as we saw, if we use a response spectrum of type design spectrum, we have to multiply the results for displacement. So in this case, I'm gonna do this in a particular way here, but there are many ways of doing this. What I'm gonna do is that I create a second analysis and I say, okay, if I multiply again by a behavior factor Q, then I get this. Yeah. And I'm gonna use here this scale factor definition. So if I multiply again by the behavior factor, I'm gonna get the correct results for displacement. Okay. Okay, I accept this, and now I can run my response spectrum analysis. I'm gonna jump into the presentation once again, and okay. Now we can make the activation of the building model add-on. Before running our response spectrum analysis, I'm gonna make the building stories definition and the floor diaphragms modeling according this section 4.3.1, and I want to show the influence in the model analysis of this. This floor diaphragm modeling makes reference to a very famous assumption in seismic design or seismic analysis, and it's the so-called rigid diaphragms. I want to say that it is not a better or a worse definition. It's difficult to make a general rule. Either we have to use this in our case or not. There is a condition here, physical condition or a clear rule where this assumption can be implemented in the model, but as a general, this is a very engineering concept and interpretation, whether we are allowed to use this or whether we should use it. Yeah. I make just reference, but as I say, if you are in a case in which you might want to implement this, my recommendation is to run a couple iterations, as I'm gonna do right now, and try to have a feeling about the results and try to make an interpretation whether it is appropriate to consider this or not, or what are the effects of this beyond it's typical to do it, so let's do it. It's always advised to take care with all these assumptions. Each building is particular, and it's not possible to formulate a general rule. Okay, and also here in the activation of the building model add-on, we can define walls. Okay, I'm gonna activate this. Once again, here, edit model based data. And okay, there was already a definition. Okay, so building model. When I activate this, I get here in building model this object or this folder, and I can edit the definition. Yeah. So I had here a predefinition with the two different stories with 4, but I'm gonna erase this in order to display how it works. So in this case, I erase the building model, yeah, and I'm gonna create, or I'm gonna generate building stories, so from scratch, yeah. Then I go to edit, and the program automatically recognized the different floors, yeah, or the planes of the horizontal element. So with this automatic definition, we can save time in the definition of the stories, and it's quite useful to have this menu definition. Now we can make here adjustments or global adjustments. In this case, I'm gonna leave this as it is. Floor diaphragms, I'm gonna consider no assumption in the stiffness, so I'm gonna leave original stiffness, and I have a second model with the rigid diaphragm, and we can see a basic difference between these two approaches. Okay, so I'm gonna leave there, and I'm gonna run this response spectrum analysis. It takes not that much time since the model analysis it's already available. Okay, here we can see like the progress bar and always an estimation about the remaining time. Okay, so here, okay, here I have the same model so far, but with a model definition of rigid diaphragm. Yeah, I want to show this for comparison purposes, so I'm gonna use window, tile vertically, and then I'm gonna close our first model. Okay, and then once again I'm gonna go here for okay, just takes some time. Window, okay, tile vertically. Okay, so we have on the left the results for the model without rigid diaphragm, and in this case I want to display once again the results for model analysis, and in this case I'm gonna use this result for masses. Yeah, what we see here is that according the here the mesh settings, yeah, we have some mesh settings on the program, and with this basic definition we have a mass definition on each point of this mesh. Yeah, so this is quite complex mass matrix definition, and if we activate the option of rigid diaphragm, I'm gonna show here, we get a very quite simplified description of the mass matrix. Yeah. So in the first place, I want to show you the definition in the building model add-on. So in this case, I have the same definition, but I selected all stories and I created or selected the rigid diaphragm, yeah, floor diaphragm as rigid. Okay. I already ran the analysis just to save time, and in the same way I'm gonna look for the results of the model analysis iteration number 3. In this case, once again the masses definition, and we see a huge difference on the masses definition. Now in this case we have what we call lumped mass definition on the center of the element, yeah, or of the floor. So this helps a lot in the analysis time for this model. No? Okay. Once again, it's important to keep in mind that this has to be analyzed whether it's better the option on the right or on the left. There is no general rule for this. Okay, I'm gonna jump on the model on the left and I'm gonna show something. It's the walls definition. So I'm gonna make a new shear wall definition. There is already one, and this is quite versatile because I only have to select the surfaces and the program it's gonna recognize the geometry of the wall. So I'm gonna select this wall, so I select simply all the surfaces, and the program is gonna recognize the cross-section dimensions and also the floors definition, and with this I can have integrate the results for the areas, because for design we need the results in form of a member, no? Exactly. So this is quite versatile and useful for a quick definition. Okay. Okay, I have to delete results after creating a wall, and we see here an internal element that it's gonna integrate the results for all these areas. Okay. Okay, at this point I'm gonna close this model, and I'm gonna stay in the reject diaphragm model for the last part of this section. Okay, I come back here. We activated our building model add-on, and now we have to check the requirements for the limitation of interstory drift. So according the floor definition, I made here the multiplication, yeah, and our limit is gonna be 35 millimeters. Yeah? I'm gonna select brittle materials for non-structural elements, and in the first place I have to check the requirement of P delta effects. Yeah. Okay. And finally, we can provide, or we can deliver the results for design. Okay. So here, important, if we are gonna check displacement results, remember we have to use the multiplied displacement from the response spectrum. Yeah. So in this case, once again, I have to use the response spectrum analysis definition with the scale factor. Now, quite important since the beginning of today's presentation. Okay, I'm gonna run this analysis. Oh, sorry. Yeah. So, okay, it's already there, the analysis, and in this case, with the spectral analysis and the building model, we have a additional table of results, and this is what we are gonna inspect right now. Yeah. And this is the entry results by stories. In results by story, we have this group of tables with quite important quantities of centers of mass and rigidity. So particularly the calculation of center of rigidity is quite particular. We have to take into account the shear walls and the particular stiffness of each column. So this is a very good result or summary for our structure. In story actions, we have the summary of story forces, its delta, and the location of resultant story forces. So for checks of stiffness irregularity, if it's required, this table provides the base information for it. So quite useful also. And here we come to the important topic for today, interstory drifts. But as we saw in the presentation, we have to check in the first place the sensitivity coefficient. So here I'm gonna check that in which case we are. So all results are smaller than 0.1. So this means we do not have to consider the limit or the P delta effects. We do not have to consider, not to be taken into account. Okay. And now, so the 35 millimeter limit. Yeah, this limit can we check in the interstory drift table, and here the program is showing the 2.88. So please take into account or keep in mind always multiplied values. Yeah, so we go for the load case 7, And in this case, we are gonna get our final result for the displacement check. In this case, we see that in the floor or in the story number 7, we have a value of 34 millimeters, and we are quite on the limit. Yeah. So I made several iterations to in the cheapest way or with the smaller sections achieve this value. Yeah. So, and of course, this is the objective of the design now, the most economical way to fulfill the requirement now. Okay, so we can say that this part it's oh, sorry, here. So this part it's done, and after this we can see how we provide the design add-ons with the information for design. No, in this case I already did it, so we can activate the concrete design add-on, and in accordance to this we can create additional design situation, in this case seismic, or in this case permanent and transient. Important is that when we have seismic and we want to consider response spectrum results or response spectrum analysis results, we have to use a result combination. Otherwise, we cannot consider these results. So in result combination, we get 2 because we have 2 response spectrum analysis. And after this, I can go to the table design or concrete design and make the definition. I'm gonna make here input data, so we can select what we want to do. Here, very important, just we have separate webinars for this, but here I just want to mention that in concrete design and on settings, you select the seismic configuration. This is not by default available, okay? And as I said, you can make a complete definition here, yeah? Okay, in this case, I can check the results in general. So in this case, there are some seismicity checks that are not considered, that are not fulfilled. And I just want to say there that in the input data, in the size situations, I selected the result combination 1 and 2, but the second is considering the multiplied response spectrum. So in this case, I made this on purpose because this cannot be used for design now. In this case, the definition should be like this. We have to ignore this. This is just for displacement. Yeah? And this is the reason why we have some design ratios that are bigger than 1. Okay, very quickly, I'm going to show now what we can do here in the next chapter, and this is quite summarized. So procedure without building model add-on. So we can do very few things without the building model add-on. So the first part we can do, and basically all the features that we saw here, we cannot do it. Yeah. This means that we have to do a very manual procedure. So for example, exporting to Excel and then making calculation by hand, I mean in a software, but manually making all the definitions. So the only quantity that can be generated without building model add-on are the story forces. Yeah, and for this you have to make the following, and this is, so I created a result beam. This result beam has no influence on the stiffness or of the building or of the structure, so it's gonna be ignored, and this works as a integration element. Yeah, so I selected here integrate stresses and forces from listed objects, And on each floor, I selected the walls. Yeah, in the first floor, so all the walls for the first floor, and then all members, or in this case, all columns for the first floor. Yeah. And by doing this, I can integrate the results on each floor, yeah, for each result member. Okay, I'm gonna isolate this just to have a clearer view. And what we see is that, for example, here in the first floor, we can recreate the 1602. We see here that it's the same value now. This is bottom, and then top is the 1505. Okay, it is the same result. So if I change here internal forces direction and the other direction, I get exactly the same values. So I say this is the only result that we can reproduce. So use as a summary here, all these other values we cannot automatically get results from RFEM. So we have either export to table and make a manual definition of it. Okay, so that's why the building model add-on is quite useful. Okay, and well, design can we do as I previously showed. Okay, use here the final remark. So, and as a general conclusion, so our hint for optimization process and iteration process. So I always mention that for the model analysis, we have to make maybe 1, 2, 3 iterations to have a sense of results. Yeah, also integrated with the assumption in the building model add-on. And also, for example, the 2 results for the response spectrum. As we have an example here, after this we have to make a design, and if we do not fulfill something here, we have to go back to change probably dimensions in the elements and go back to carry out the whole design again. No, if I make a change in the dimension of this column, then I have to go back and run again the model analysis and the response spectrum analysis and perform once again the design. So for this iteration process, very intrinsic from seismic design and seismic analysis, a given condition, this iterative process, so our program offers a very versatile and very useful approach with our design add-ons. No? So our philosophy, all in one, you can apply by activating and selecting what you need. In this case, we made use of 4 add-ons, and you don't need an additional application for this. No, that's why RFEM. So it's very useful for this. Okay, that's the final conclusion on this topic. Drift limits or inter-story drift limits. So in this case, I give back to Andreas, and so thank you for your attention. So Andreas, you can take the presentation or retake the presentation.
Thank you, Victor, for your nice presentation. Yeah, at the end, I have an additional hint for you to our online courses. You can book them. For example, the RFEM 6 course. That's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design with RFEM 6. Then the Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design, and the Eurocode 8 course for the earthquake design. For more information and prices, just scan the QR codes or click at the buttons on the bottom. Okay, yeah. Only a further hint. Yeah, that's a hint from my side. You can get such a course for free. Just send us a customer project, and when we publish this customer project as a gift, you will get such a course. That course that is valuable for you. Now just write an email to info@dlubal.com. Then I will write you what files I need. It's not so many work for you, I promise. Then into our free online services. You can join the Dlubal community. Then you can use the GeoZone tool. Some clicks are for free. Then you can get cross-section properties on our website. You can download 3D models. And if you want to know more about our free online services, just scan the QR code or press that link here. If you don't use RFEM 6 or RSTARP 9, you can download a trial version that's valid for 90 days with all add-ons. More information can you find on our website, dlubal.com. For example, the knowledge base articles. You can ask the Mia AI assistant all the day and all the night, 24/7. Just ask her and she will answer you. She knows all the content from our website, such as the knowledge base articles, FAQs, and so on. That should be also all from my side. I thank you for your attention. Thanks to Victor for the presentation. Thanks to Thomas for the help by answering the questions. I wish you all a nice rest of the day. Bye-bye.